Today we are discussing roots, intercepts, and multiplicities. So we've already discussed all of those, but there's a few things that you are required to know. First, if you have roots or zeros, you would write them as x equals. So if I ask you what are the roots or zeros, your answer would be, for example, x equals 3. Now, if we're asking for y-intercepts or x-intercepts or y-intercepts, you must write as a point. So in this one, so even though x equals 3 is the same thing as the x-intercept of 3, 0, it depends on what's being asked. So it's a little nitpicky thing that you have to keep track of. So everything that we've been doing up till now has always been x equals 3. But the moment I ask for an intercept, you have to write them as a point. So you basically just have to know that if you're looking for a y-intercept, that the x value is 0 and the y value is some number, etc. So these are just examples of how you would write them, but that's just the idea. All right, multiplicity. When you're doing multiplicity, we have discussed this. If you have a multiplicity of 4, for example, for this one, the 0, 3. So remember, if you were to t-chart that, x minus 3 to the 4th, if you were to t-chart this, you would set this equal to 0, add 3, and x would be 3 in this case. But that 3 happens 4 times. So when a root or a 0 happens 4 times, special things happen at the root, at that spot on the graph. So that's what we're going to be discussing today. So you already know that this happens 4 times, but what happens with the specialness of it that we're going to be discussing today. So this 5 here has a multiplicity of 1, and this x plus 8 has a multiplicity of 2. So that means that the negative, 8 is negative, and when it's a root, and it has a multiplicity of 2. So just as a reminder, these guys are factors. Each one of these, x minus 3, x minus 5, and x plus 8, are your factors. When you solve them like this, you get the solutions or the roots. Okay, so what happens at these roots? What's the specialness of the multiplicity? Well, nothing truly special happens when x equals 1, when the exponent is 1, or has a multiplicity, like x minus 5 here, it had a multiplicity of 1. That just means it would have cut through the x-axis at that spot, just normally, just like a line would. If it's squared or any even exponent, it's going to bounce off. So it could either bounce at that spot in the positive side, or it could bounce at that spot at the negative, on the negative side. So it would, be like a parabola going up or a parabola going down. So that's if it's an even multiplicity. And then an odd multiplicity is these, where it kind of just like jogs through a little. These aren't, just do your best drawing that when we have to draw things like that. But if it kind of cuts through in a spinny way, almost like this is a concave up parabola, and then it shifts to a concave down, that's when this one is considered still an extrema point because it's not increasing or decreasing, but it's not a line. So you have to kind of make it all squiggly. So what does that mean? Well, that means we can look at a graph and determine its least possible roots. All right, so we can look at a graph and its multiplicity, and we can look, where does it hit the x-axis? So this one hits at -1. It hits. This one hits at 1. And this one hits at 2. Now we know from its end, okay, so what are the roots? Sorry, that's what I figured out. What are the factors? Well, the factors are, you just add the 1 here. So x plus 1 would be the factor. This one would be x minus 1, and this one would be x minus 2. So these are our 3 factors that those roots came from. So then we have to ask ourselves, What is the minimum multiplicity of each? So that's when we have to look at what's happening at this point. So this one comes from this point right here. Is it cutting straight through? Is it bouncing? Or is it jogging through? Well, this particular one is kind of like doing a little squiggle, does a little pause here and then goes downhill a little more. That would mean that this would have to be an odd. So this would have to be some sort of odd number. Now, if we're doing least degree, then it would have to be 3. Okay, because this one right here, this cuts through like a line, and that is always 1. The number 1. So there is no multiplicity for that one. It just has 1. This one right here, since it hits and stays on the same side of the x-axis and it just bounces right off, this is going to be even. So if we're doing a minimum multiplicity, the odd minimum would be 3. The even minimum would be 2. And that one would be 1. So that means that this would go here. This would go here, and the 1 would be there. Okay, so if I were to write an equation, it would be that. So now when I do this, what is the minimum multiplicity of each? Well, we figured out 3, 2, and 1 for these. How many total real roots? Well, this has x, there's 3 x's in this one. This one has 2. And this one has 1. If I were to multiply this whole thing out, there would be, the degree of this polynomial would be 6. The degree would be 6. So this has a total of, whatever. What is the degree? So that's that question. How many total real roots? Well, there's 6 real roots, but, because of the multiplicity, we only have 3. So the answer to how many total real roots is 6. That's the same question as what is the degree here, this one. Determine the sign of the leading coefficient using the end behavior. So discussing end behavior, you have to ask yourself, the 2 questions. What happens when x is going to the right, and what happens when x is going to the left? And we're not talking about all the squigglies that happen here. So in this case, all these squigglies is middle behavior. Okay, we want end behavior. We want to go into the ends. So what happens, okay, it does all this, but then it settles down and it kind of balances out. When x is going this way, then we know that f of x, or y, is also going up. This one, when x is going this way, the function is going down. Oh, yeah, because I'm crazy, that's why. No, the function is always going up, okay, because the parabola is going, or whatever, this graph is going up, both when x is going to positive infinity and negative infinity. So from this information, I know this has to be a positive leading coefficient. So this one is good. So I don't have to put any sign right here. I know that it's going to be positive. Okay, next. All right, so now we're going to kind of go the opposite direction. Can I give you an equation, and can you write, can you draw the graph or sketch a graph? Now, we're going to talk about the difference between sketching and graphing in just a minute. So for this problem, how we want to go about doing this is we want to look here and determine how many x's there are. So what if I were to actually multiply this sucker out, what would the degree of this one would be? Well, this would give me a quadratic because it's x squared, and this would be a cubic, it'd be x cubed. So altogether, if I multiply those together, I would have an x to the 5th equation. So I know that this is going to be have odd tendencies. Okay, so determine the end behavior using the leading coefficient. So I know this is x to the 5th. So I know it either has to go like this or like this. It has to be in that direction. Remember, even even is like the one that we just did on the back of this. Even is going up or down, where they both go up, up, or down, down. So what we need to do is, I know is it going to be up, up, or is it going to be, is it going to go up or down? So determine the end behavior. So it's the leading coefficient here is negative. So if it's a negative x to the fifth, you know that it's going to, the whole function is always going to go down. So that means that we're going to have going down here and here. This function, just as a brief sketch, is going to look something like this. So you know where it has to kind of start and end there. Let's get rid of those. Okay. So next thing we want to do is sketch that in pencil, which we just did. And now we want to mark the roots on the graph. So we have two roots because we have two of these nice factors here. So one of the roots, just T-chart that basically what you're doing. So you're getting x minus 1 equals 0 and x plus 2 equals 0. So add 1. So x equals 1 and x equals negative 2. So I want to put 1 and negative 2 on the graph. Right, based on, I did that, find the y-intercept. So to find the y-intercept, remember y-intercepts are where x equals 0. So we simply have to plug 0 into this equation right here. So I have to plug 0 in for x, which is not too hard. So it'd be negative 0 minus 1 squared and 0 plus 2 cubed. And you just have to do the math here. So this is negative 1 times 8. So it would be negative 8, and we plot that on the graph. Negative 8. Okay, so I know it has to go through that. It just makes my graph a bit more accurate. So this point would be 0, negative 8. All right, now to do this, use multiplicity to graph the behavior at the roots. So this root right here, or this factor, has a multiplicity of 2. Okay, so that means that right here, it has to bounce off. Well, the question is, does it bounce off this way or does it bounce off this way? Well, that's what the end behavior was for. The end behavior told me that in the end, this thing needs to be coming down from here. So I'm going to have it bounce this way. Then it's going to come through this root somehow. That is pretty. Things are never pretty when you do these. All right, and then for this one, x plus 2 equals 3, you know this is x plus 2, so we know that it has a multiplicity of 3, so that means that it's going to kind of jog through, so it has to go like this and this. All right, so you may want to get a little bit more accurate there, but that's the way it is. So we're going to be discussing what it means to graph and what it means to sketch. And basically what that means is a graph is very picky. So if I tell you to graph something, I'm going to be very picky when I look at the little points. Okay, so graphing this one specifically, I probably should find this minimum point here, this extrema, and graph it accurately. Okay, so let's just talk about that for a second. So if I ask you to sketch, I'm going to be pretty easygoing with everything. So labels, so you probably want to label your x and y axis. And if there's more than one graph, then you're going to want to label a graph. You're going to want to plot the roots, but you don't have to label them. The extrema points don't really matter. You might want to get a somewhat accurate, but we don't really care about extrema points. Intercepts should be fairly accurate. If you're going through an axis, then you should probably have a good one. So if you're going through the y-axis, make sure you plot the y. And arrows, yes, you should have arrows. With a graph, you want to label everything. Plot the roots. Extrema points must be very accurate. So that just means that you should look at it in your calculator and use your ability to find the max and the min pretty calculator. So sometimes they're decimals, but you should put them in a fairly accurate spot. Absolutely, these should be accurate. And always arrows should be close to the last points. Okay, so what I mean is if I'm graphing this one above here, okay, see how close I put these little arrows? That's what you want to do. It's pretty much a joke that they're asking you to do this, but sorry. Don't tell anyone I just said that. So I want to make the arrows really close to these points so that none of these extra points that are here, none of these extra points that I draw could possibly be determined as inaccurate. So graphs, very picky. Try to just do everything in your power to make sure that everything is accurate. All points are good. Sketching, you just want to get a basic look of a graph. All right? So we'll practice that a little. Have a great day. Because you guys are awesome.